Assalamualaikum warahmatullahi wabarakatuh and hello everyone. In this video, we're going to discuss week 6 hour 1 tutorial, which is the last tutorial for electrochemistry 3.3 electrolytic cell. Our learning objective for non-face-to-face questions is to apply Faraday's law in calculations. Electrolysis of concentrated potassium iodide Ki solutions was carried out by using inert electrodes. So you need to draw and label the cell. So for electrolysis, we're going to use the setup of electrolytic cell. We're going to start with a beaker containing solutions, which in this case, the potassium iodide. So don't forget to write the states of these solutions, which is the aqueous. And then we have electrodes, so we're going to use inert electrodes of platinum. You can also substitute platinum with graphite or palladium. And again, don't forget the phase here, the solid. And then these two electrodes will be connected by using wire. And on the wire, we're going to attach a power supply and also ammeter so that we can measure the current flow. So, movement of electrons is always from anode to cathode. Let's say we have anode on our left hand side and cathode on our right hand side. But then the additional feature in this electrolytic cell gonna tells you that the assignment of positive and negative terminal in this cell gonna be a bit different from the one in voltaic cell. We know voltaic cell requires spontaneous reactions. Spontaneous reactions comes from the electrode and also the electrolyte. But since electrolytic cell uses inert electrodes, means the electrode has no ability to attract or discharge ions on its own. So they need this power supply of this battery to help them to attract the ions. So look at this symbol where we have longer and shorter line at once. So this longer line indicates positive terminal of the battery, while the shorter line indicates a negative terminal. So we know that the inert electrodes has no ability to attract or discharge ion, means in order to make the electron to be flow from anode to cathode, we need to attract opposite charge of the terminal. So look at this negative terminal of battery. They go straight forward to the cathode, indicates that the cathode gonna have negative terminal while anode gonna have positive terminal. So as for this cell, cathode will attract cation and anode will attract anion. B. Write the half cell equations at the anode and the cathode. So let's recall again, we have a solutions of potassium iodide. So whenever we have aqueous states, means there will be water molecules present in the solutions. So in order for you to indicate who's going to be attracted to the anode and cathode, we need to first list all the possible cation and anions. So for these solutions, we're going to have K plus, I minus, and also water molecules. Okay, so anode is the positive terminal. They will attract opposite charge of an ion. So our anion in this case will be iodide and also water. So water, we should take the value with more positive value as suggested by the positive terminal. While for cathode with negative terminal, they will attract cation of K plus and also water. So water in this case, we're going to take a more negative value due to the negative terminal. So between these four possible ions, we need to take only one at each electrode. So we're going to look at the value of E naught given at the end of the equations. So for anode, because we're going to conduct oxidations, then we need a more negative value. So from these two ions, we are going to take the I minus because they got a more negative value. While for cathode, we're going to take a more positive value, which in this case, the water. So then we're going to combine these two half cell equations in terms of oxidations and reductions and make sure the number of electrons is already tally with one another so that we can cancel them out. Lastly, our overall equations will be 2I minus aqueous plus 2H2O liquid to form iodine solid and 2OH minus aqueous together with the hydrogen gas. As for question C, they want you to calculate the mass of iodine that will be deposited if 10.5 milliamp of current flows through the cell for 100 minutes. So we are given information regarding the current and also the time. So we are going to apply Faraday's law of electrolysis whenever we are going to do some calculations in electrolytic cell. So we need to first find the charge that we use throughout this reaction. So we're going to use the formula of Q equal to IT. The I must be in amp, so please have a look at this prefix of milli, and also the time taken should be in second. Then we need to do something with the minutes here. So once we substitute the value, note that I've already changed the milli to 10 power of negative 3, and also the minutes to be changed to second by multiplying it with 60 seconds. And lastly, the charge for these reactions is 63 coulomb. In order to find the mass of iodine, we need to find the mole of the iodine itself. In order for us to find the mole for this 63 coulomb, we need to relate it to the theoretical value. So we somehow need to relate it to the half cell equations we have wrote earlier. We have 1 mole of I2 with 2 mole of electrons. So 1 electrons is represented by 1 Faraday. If we have 2 electrons, means we're going to relate it to 2 Faraday. 1 Faraday is equal to 96,500 coulomb. And then we're going to do a bit of stoichiometry where 2 mole of electron comes from the I2, going to have 193,000 coulomb. What if we have 63 coulomb? So we're going to do the cross multiplications. Then we'll get the number of mole of I2, which is 3.264 10 to the power of negative 4. Lastly, we can simply calculate the mass of iodine. Note that the iodine here is not just I. The mass given here is only for I, but you have I2. So please times it with 2. And lastly, you'll get a mass of iodine deposited of 0.0828 gram. For learning objectives face-to-face questions, you need to know how to apply Faraday's law in calculations and to set up electrolytic cell and determine the Faraday's constant. Zinc plating is an important means of corrosion protection. Calculate how many grams of zinc can be deposited on a steel tank from a zinc sulfate solutions when a 0.755 amp current flows for 2 days. So we have exactly the same structure as in non-face-to-face question just now. So we're gonna first find the charge that we use in these reactions. Then only we can do a bit of stoichiometry, and lastly to find the mass. So we're going to use the formula of Q is equal to IT, and then we already have current of 0.755, so we don't need to do anything. And as for times, we need to change it to second. So we know that 1 day equal to 24 hours, so we need to times it with 24. And for every hour, we know that we have 60 minutes. Then we need to times it with 60. And for every minute, we have 60 seconds. Then only we can find the seconds, time in seconds. So once we do this, we're going to cancel this. Now we're going to cancel this. And lastly, we're going to cancel with the minute, leaving only seconds. Lastly, our charge for these reactions used is 130,464 coulomb. As for the theoretical value, we are going to write the half cell equations for zinc. So we are going to form zinc means we need 2 electrons. So as we've already done earlier, 1 electron is equal to 1 Faraday. So 2 electrons is going to be 2 Faraday. So 2 Faraday is equal to 193,000 coulomb. And the number of mole for zinc for 130,464 coulomb will be 0.676 mole. Once we've got the number of mole, we can simply times it with the molar mass of 65.38. Then lastly, the mass of zinc deposited will be 44.2 gram. For question 2, a current is applied to two electrolytic cells in series. In the first, silver is deposited. In the second, zinc electrode deposited. So calculate how much silver is plated out if 1.20 gram of zinc dissolved. Please be reminded, whenever you are given cells connected in series, it means that they're going to share exactly the same charge. So even though information given in the questions is about zinc, we can still figure out the mass of silver down here. So first, we need to split it into two electrolytic cells where we have silver deposited and also zinc deposited. Since we've got the mass of zinc, then we need to start with zinc. So mass of zinc can be divided by its molar mass, then you will get the number of mole of zinc. From the number of mole of zinc, we're gonna find the charge being used by relating it to the theoretical value given from the informations of this number of electrons. So we know that 1 mole of zinc equal to 2 electrons, also equal to 2 Faradays. So 1 mole of zinc will give 193,000 coulomb. As for 0.0183 mole zinc, we're gonna cross multiply the value and we'll get 3541.28 coulomb. So we're gonna use these informations here and then use it in the silver electrolytic cell because they are connected in series. So from the half cell equations of silver, we know that 1 mole of silver will have 1 mole of electrons. Therefore, 1 mole of silver will require 96,500 coulomb. As for 3541.28 coulomb, require 0.037 mole of silver. So from this number of mole, we can simply times it with the molar mass of silver, which is 107.87. And lastly, we'll get the mass of Ag deposited as 3.96 gram. We have completed all the tutorials for Chapter 3 Electrochemistry, so you may now proceed to do the past year's questions and also your revisions. Thank you.